Great. So this one is shorter, and this one is less technical. So when I prepared these slides, it turns out that basically this is the whole color graph graphics stuff, and all the heavy algebra went for the first. I don't know. So probably that's how it goes.
Let's wait another few minutes.
So I guess we can 2-3 minutes, and we'll see how many people will be there.
Moxen is in.
Hi, Moxen. Are you driving or?
Hi, I'm driving. Hi.
Hi.
Oh, you are driving now to Indiana?
Yeah.
Oh, listen, focus on driving, please.
I listen to the talk, so I don't have any problem.
Okay.
Yeah.
Hope you don't crash, because if so, Wojtek will blame it on me.
Of course. Okay. Okay, when we get 10, when we go to 10 participants, we'll start soon.
Sure.
Okay, Krzysztof, you can start. This is the second part of dynamic network. And Dr. Turowski will tell you a little bit, probably some experiments, see whether you can relate to them and talk to him and continue some working. Thank you, Krzysztof.
Thank you. Okay, so the topic of today's talk will be continuation of what I presented last week, but with more on empirical twists. So first, I burdened you a week ago with heavy algebra and quite boring and tedious formulas. Now it will be more colorful, less rigorous, as I must admit at the beginning, and on the other hand, it's more art than science on certain fields. So for example, here, what we would like to do, three things. And these are practical problems that can really have certain impact. For one, we want to have parameter estimation for real-world networks. So suppose that we ensured ourselves, as best as we can do, that that certain model is a suitable fit for a certain network. Oh, we have certain arguments for this claim, and we would like to find what exactly should be the best parameters under this assumption then that this network comes from this model. And this is some kind of an inference problem, Yet it is a very special problem because on the one hand, you have very limited knowledge. So for example, at worst, you have just one sample. So we have one graph, which stem from a particular model, and you would like to guess its parameters. It is so how much you can squeeze out from one sample? Not much, but using some secondary assumptions, you can arrive at certain reasonable parameter estimation procedures. The second is temporal clustering. So as I was describing the model, you'll notice that the model is defined in terms of incoming vertices. So first vertex comes, so we have some starting graph, then a vertex comes, then next vertex comes, and so on. And then we would like to uncover, given the final state of the graph, so we have certain structure, we would like to uncover the order, in the best case, the whole order in which the vertices came, arrived at the graph. And the problem is that we are not able sometimes to recover the whole ordering, and we will be satisfied with something which is a partial ordering, not a full ordering. So we certainly tackled this problem too, and we arrived at certain conclusions. And the third, of course, probably the most important and the most practical of all three is compression. And here we have one special case in which compression is doable for the duplication divergence graphs, which I'll talk at the end. So whenever we have real-world networks, we call this a family of goodness of fit problems. And we would like to fit certain networks, as I told you, to certain models. The main problem here is that we can describe this evolution of dynamic graphs, and especially for duplication divergence graphs, as some kind of Markov process. So the next state only depends on previous state, given certain matrix of probabilities of transition. But the problem is that the process is not homogeneous, and it is non-stationary. So it, of course, is non-homogeneous in that sense that the transition matrix in each step becomes one dimension higher. And of course, non-stationary because it is not usually the case that we arrive at some steady state. Okay, we have certain auxiliary problem that's, as I told you, that we would like to guess, well, rather to estimate, to make an educated guess about the parameters under the assumption that certain network comes from a given graph model. And when we did a review of the literature, it turned out that there is a very simple procedure using some kind of technique called mean field approximations. It is easy to spot that it was developed by physicists. On the one hand, it is very simple, very nice, and it clearly can be computed quite easily using numerical methods that we can get given gamma. So given the scale parameter that we can estimate and given the average degree of the graph, we can recover from this system of equations both P and R as parameters to our duplication divergence model. That you remember, it had, no, in fact, it had 3 parameters, but we have number of vertices we have already fixed, and we need to recover P and R. So there is a very simple formula, and people apply it. However, there are certain problems with this technique called mean field approximations, as physicists often like to simplify things, and especially when they tackle network science, it is very apparent whenever you compare works on network science in physics journal and in computer science journal, that they do not care about the proper proofs of certain theorems, and they very often rely on the higher order approximations that, unfortunately, at some point they even go into areas which are not precise. So they, for example, they claim that some theorems are valid in the whole range whenever there are some certain boundaries where they do not hold. And there is another problem, and this problem is more related to the whole idea of scale-free networks, that actually whenever we are given some network, it is really hard to estimate the tail exponent using simple methods that are customarily assumed. That's typically the idea is as following: that okay, we allow that a large fraction of the graph with especially the vertices with low degree, they do not follow power law, but power law, at least in its feasible form, kicks in at some point of the spectrum of degrees. And the problem is, how do we compute? And whenever we looked at the data, it turned out that 95 to 99% of data were thrown out just because of this property, right? That we were looking at the estimation of scale parameter, and it was given from the tail of 1-2%. And whenever we try to increase it a bit, the results were in fact very unstable. So the parameter gamma that was derived using the formula above was really changing, and this of course influenced the whole result, the parameter estimation of PNR. And that was the first problem that we encountered. We tried to replicate the results existing in the literature, and we found that, well, maybe this cutoff point is problematic. Then there is a second point. There is a second problem, and the second problem, I'll probably have it in a minute. So we decided to do it rigorously, and we went through the series of recurrences, and you probably remember from last week's talk that we had certain recurrence on the average degree and on average degree squared. And here we arrived at certain few more recurrences, for example, number of triangles and number of open triangles in the graph. And here we have this for pure duplication model, that is the model when we have only P, but R is zeroed out. But we can arrive at similar formulas, although slightly more complicated, for the model with P and R. And these we can find with, it's some kind of distributed algebra that I threw at you last week, but in principle we can get at them, and we can use them to form recurrences for the whole model. And given the starting point, given the end point, we can iterate these recurrences, and we assume, for the sake of simplicity, so this is one way or another, it's unavoidable, that we are somewhere near the average state. Then we can compute P and R using numerical methods from these. These functions are, fortunately, they should be monotonous in P, if I remember. So fortunately, the estimation is not problematic. With P and R, it's more of a problem, but nevertheless, we can use numerical methods to arrive at decent results, to decent sets of parameters P and R that are sufficiently close for our purposes. Okay, and whenever we try to fit it, we arrived at something like that. Here we have, in fact, we have 4 curves, but degree squared and open triangles are almost ideally matched. So there's very tiny difference. And the fact is that degree squared and open triangles are very closely related by a linear factor. So in fact, whenever we compute expected number of open triangles and an expected degree squared, they in the estimations, they give the same sets of parameters. And these all these curves represent the sets of parameters that are suitable from point of view of this particular parameter. So whenever we take recurrences, for example, for triangles, expected number of triangles, we find that there is a set of P's and R's that are suitable to get from starting point to the end point. And this set of points forms exactly the curve that it's visible. And here we notice that that there are certain numerical errors that are problematic, but in fact all the curves meet near one point. And here is one example, but there are also another examples from another data sets. And it was the rule that the area between the crossing points was very small. So we estimated it near this meeting point. In fact, we used certain area, which was we call this a confidence interval. So technically, from statistical point of view, it is not a confidence interval, since definition of confidence interval depends on the number of samples, and here we have one sample. But we used the fact that we allow ourselves to be 10%, so some kind of few percent above or below the average value. So we do not consider ourselves that we hit exactly the right value, but we can be somewhere below, somewhere above. And then we were looking for the sets of points that conform to this measure, and we found also that there are sets of points, and here you have examples on synthetic data, but actually the fit was quite close. That whenever we have a network which was 100 vertices with parameters p equal to 1/10 and r equal to 3/10, actually the crossing point is okay. It is somewhere above 0.11, but r is pretty close, and p and r are really within 10–15% of what should be. And on the other hand, whenever we set p and r significantly higher, so to 0.99 and 3.0, it was also the case that the crossing point was really close. Okay, but we have this technique, and maybe someone would like to ask, why don't you use a standard technique that was developed earlier, that is maximum likelihood? And the whole idea is that, okay, we have this this Markov chain. It is inhomogeneous, we know it, but we can form a certain formula that's this product that, given certain zero hypothesis parameters θ0, which can be taken as arbitrary, we can compute formulas for creating under our set of parameters or our guess θ. We can compute formulas. How probable is it to get from the graph gk-1 to gk? And we can repeat it. And of course, we can repeat it from our starting point to our ending point. And we can look at it in the whole spectrum, and we can compute the expected utility, the expected value using the what's called the importance sampling method. And if we do so, then we arrive at each point θ. We can arrive at maximum likelihood measure, and we can pick the best one. And it turns out that we performed such experiments, and it turned out that the results were very similar. There's one small caveat, that in fact, the recurrence approach requires us to do, especially when we were looking, for example, for the curves only. So we used exact values of the mean. It required us really to, that depends how many samples we did, but it required us to pick a certain value of p, and then using the convexities, we just needed to do some binary search for the proper point, and so depending on the precision, we have the number of samples which is linear to the scale, the number of points on the p scale we've chosen. And of course, it is proportional to also to n or to t, so the number of vertices in the graph. The problem with maximum likelihood is that each point for each given theta requires us, in fact, requires us to do computations which would determine the probability of creating graph GK from GK minus 1. And how many possibilities we have? We have n possibilities, because at each step, each vertex can be chosen as the last vertex, the vertex newly added. And for each, we have to compute the transition probability, we have to compute the weights, and we have to add. And then we, of course, we need to recurse on that. And that's the problem, that whenever we have this product, actually what we need to do at this numerator, so we have here, we have to sum them, and since this is the expected value and we do it by sampling, at each point we have to reduce graph GK or its transition matrix to the transition matrix of graph GK minus 1, GK minus 2, and so on. And we repeat this process. And all in all, I still have a certain hypothesis that it can be doable with some clever bookkeeping, well, strictly less than n to the third. But the problem is that so far we looked with both Wojtek Szpatkowski and Abraham Magner that we got to the n square. We didn't get to n square, we got to n third, and as at each step we have to compute n square matrix from scratch. Or in fact, this matrix should be k rows, k columns at each stage. No, so it is n third. If there is a clever way to do the bookkeeping, we can lower it a bit, but at least it has to be n squared time. And recurrence, it's linear, so it is much faster. So with maximum likelihood, you can compute, let's say, hundreds, and with recurrence approach, you can compute hundreds of thousands. So that's basically the difference. Okay, and here you have comparison with the same methods. So the method of maximum likelihood comparing to our approach, and we see that here we had quite a good match, and here we also have quite a good match. And it turns out that both methods are good in practice, but maximum likelihood, unfortunately, is too slow to be used for the scale. So for the size of the data that we are considering. So these are, let's say, around hundreds of thousands. And we basically what we did is we applied it. And one other thing that we did is we combined it with computation of automorphisms. That all you know probably that of course degrees, triangles, open triangles here called wedges are the measures which are in some sense informative, but they are global. So on the other hand, they are local. So whenever you have triangles, they can be spread around the graph, or they can be contained within one large clique. With degrees also, you have this discrepancy that, on the other hand, the graph which has average degree 2 can be a star, or it can be a cycle. And we know all that, so we wanted to capture another important property which would be important in this sense, and we decided to test our results comparing to these previous formulas. So with this comparing these formulas by using automorphisms, and we took parameters which were derived using mean field approximations. We derived parameters using our method. We computed automorphisms for the real-world networks, and of course we computed average degree, number of triangles, and so on. And we computed for example networks which were generated from our model using both sets of parameters. And we compared them. And it turns out that our model was pretty good in estimating. So of course it was pretty good in this sense, since we calibrated in that way, in estimating degrees, open triangles, and triangles. As we calibrated under this measure, that obviously it behaved well. But also when we took automorphisms, and it is long known that biological networks have tons of automorphisms, that in fact, under previous calibration methods, the resulting networks were either completely asymmetric or almost so too symmetric, in that sense that they generate the parameters were too low and the majority of vertices were isolated, which is also completely unrealistic. And in our case, it was that there were certain small connected components, but all in all, the number of automorphisms was pretty close. And that served as additional confirmation that we are doing something which is quite good, in the sense that it could really be the case that that this kind of model fitting really leads us somewhere. Because with this, you never know the ground truth. So we do not have an external access to the mechanism which produced this network, in that sense that we do not have a definition or a set of rules, probabilistic rules, which were laid out somewhere. But given the fact that that we have not only these parameters like degree and number of triangles, but also certain other measures, for example, automorphisms, matching, then it suggests that it may be the good way, and really the underlying model of these real-world networks may have something in common with our model. Okay, so another problem is temporal clustering. And here we have a very simple definition. We have a graph. It comes from an incremental model, or we assume that it comes from an incremental model, and we would like to find a linear order which maximizes the probability of generation of this graph according to this order. And here, when we assume that incremental model is known, we assume that it is known together with its parameters. That is, we basically made the first step, and we assume we got certain parameters here, and we assume that it is the ground truth for this model and for this network. Okay, but the problem is that whenever we have our duplication divergence graph, and in fact, I guess for all models which are incremental, whenever we have symmetric graphs, we cannot distinguish vertices which have exactly the same neighborhood. So for example, here vertices 1 and 3, they have the same neighborhoods. And I guess so any incremental model must have this property that probability of all permutations in which 3 came before 1 has to be equal to the probability of all permutations in which 1 came before 3. And it has to be exactly symmetric. Okay, so we can relax the problem a bit, and we can say, okay, we would like to have a partial order with minimum density. Okay, so it is with we just want to, for example, recover only, let's say, 20% of pairs, 50% of pairs, 80% of pairs. So we have certain threshold, and we would like to maximize to find the probability of generation. Compare that, we can answer queries. Did you came before V in this graph with 80% of answers being definitive? So yes or no, and we assume that certain fraction can be left as no answer. And of course, this is similar to the clustering problem. So in fact, clustering problem is a special case of partial ordering. Whenever this partial ordering can be presented as a set of clusters. And we assume that that we are satisfied with knowledge about these sequence of clusters for the graph. Okay, so that was our point of departure for this work. And we first, what we needed two measures of fit. First, we borrowed the notion of density, and for a set of vertices from 1 to t, we have a partial order, and we define density as a number of pairs which can be recognized under this model. And here, yeah, so the total number of pairs which are comparable under this partial order is t over 2, and we want to have density as a number of comparable pairs. And precision is that for a partial order, we have certain pi, which is our ground truth. So pi is the true order of vertices. In fact, pi minus 1 is a true order. So we have certain graph, we apply to it permutation pi, and then we get our graph, which we investigate, which has vertices 1 to 3 up to t. But we would like to uncover what was the graph before application of permutation pi to the graph. So we go with the following measure, that we have number of comparable pairs, and we would like to get the expected value of number of pairs which were guessed right. So they are both comparable in the proper way in partial order sigma, and they were also comparable in the original, so in the true ordering of the vertices. Okay, and of course, since we have two criteria, the idea is that we want to set some kind of minimum density, and we would like maximize precision for that. Okay, but with the for one example, that we have original graph, and we apply permutation pi, and here we have estimator which outputs the following relation. So it outputs 3 pairs. So 3 does not appear anywhere, but 4 is comparable to 1, 1 is comparable to 2. Therefore, we assume that so in the clustering it is trivially assumed. In the partial order, here it is assumed. In general, no, but here we assume also that it is transitive. So 4 is less or equal than 2 in this partial order. And as we look, the relation between 4 and 1 in the graph on the right is the relation between vertices 3 and 4 in the original graph. So it is correct. But if we take vertices 4 and vertices 2 in the graph on the right, these are vertices 3 and vertex 3 and vertex 2 in the original graph. Therefore, it is not, the guess was wrong in this case. And the same goes with vertex 1 and vertex 2. In the original graph, it is vertex 4 and vertex 2. And that means that this is the also the wrong guess. And of course, we have 3 comparable pairs. So density is equal to 1/2. And since we got only one proper guess, so one good guess out of 3, we have precision 1/3 for this particular partial order. And here we have expected value, because as we know, we have here we have a distribution of all the ground truths. So given a graph, we have certain probabilities that certain origins were more or less probable. And these probabilities are just weights measuring the precision of each ground. So partial order with respect to each ground truth, and we average over all of them. Okay, so we have this optimization problem. And the idea is that we would like to have, right, so this is exactly written as here. So we have certain ground truth, which is our graph GT. We have our graph, which we have access to, which is h of t. And we have certain probabilities, right? That each graph, depending on its structure, it may be more or less probable that we generated graph GT in this way. As I told you before, that due to its incremental nature, that we can arrive at the same graph using exactly at the same structure, at the same the 2 isomorphic graphs in different ways. Of course, they would have different time labels, and it is the case that they would have different probabilities. Okay, so we derived the optimal estimator, and we assume that for each density constraint, so we would like the density to be at least epsilon, we defined the optimal estimator maximizing density for a given graph. And our core idea was to derive an integer programming formulation. So we've taken as the variables XUV whenever they are comparable under this ordering phi, and PUV is exactly the probability that given the fact that our ordering given the fact that we see a graph HT, vertex U preceded vertex V in the true order. And of course, we have different possibilities. So we have different ways to generate the same graph. And in some, it may be the case. So it may be the case that U was before V. In some, that U was after V. And for example, whenever we have 2 identical vertices, we would have naturally PUV equals to 1/2 because we cannot distinguish these vertices. So PUV serves in a way as a proxy for distinguishability of 2 vertices. And we derived integer program. Basically, we would like to maximize, since we would like to maximize the probability. So we just rewritten the expression for the optimal estimator, and we arrived at that we would like to maximize the following sum. And there are certain constraints. Of course, the first constraint is, so it has to be integer programming. And in the ideal case, we would like to have all pairs comparable. So, but since we are looking for partial ordering, we would have only two events. Either u is less or equal, so either u is less than v, or v is less than u, or we have the third special case that u and v are not comparable. Whenever the first case holds that we have xuv equals 1 and xvu is equal 0, because of course it's not comparable. In the second case, we have vu equals 1, xuv equals 0. And the third case, we have xuv equals 0, xvu equals 0. So we have we can separate these three cases. And of course, there are three conditions. First is related to density. Second is related to that the ordering is asymmetric or antisymmetric, in fact, if I remember correctly. And the third one, it's transitive, right? So whenever we have two pairs which are comparable, then also the third pair has to be comparable. And we can relax it a bit, and using the assumption that we actually get here to the equality, we can make a few substitutions and arrive at the following linear program, which of course gives us the upper bound on the required parameters, and we can solve it. Or actually, we could solve it provided that we have PUV. And the problem is where to get PUV from. One thing that's important that we notice that whenever we have quite good estimators for PUV, so they are within some range lambda, then this program can be solved within range 3 lambda for any arbitrary lambda. So whenever we have good approximations of PUV, the optimum cannot move very much. And the idea is to find PUV. And PUV, of course, it's a sum over all permutations that are feasible, such that u is before v divided probability of all permutations. Okay, and we decided to use the importance sampling. I've already shown the similar formula for the maximum likelihood, and here it's basically the same idea. At each step, we have graph on certain number of vertices, let's say on n vertices. And then we can compute how probable it was that this particular vertex came as the last one. So we need to get for all pairs of vertices, how probable was that this vertex was last one and was the child or the copy of another vertex. And we sum over these vertices. And we have certain weights which are assigned to each vertex. Then we fix any arbitrary distribution Q, and this forms our weights. We pick any arbitrary distribution, provided that it's I guess it has to be non-zero whenever W is non-zero. So to be properly defined, if I remember correctly. But this distribution may be really far away from W, and given these distributions, we choose a vertex according to this distribution, and we repeat it each step as we go up to a certain point, up to certain t0, which we fixed arbitrarily. And the total weight, would be such a product. And then the idea is that by importance sampling, we can find average just by repeating this experiment a certain number of times. And in fact, it was proved that this has almost sure convergence to the true values. And the trick is how many of these estimators, so how many of these sample paths do you need? Unfortunately, empirically, we find that the convergence is not too fast, so it's actually quite slow, although this is not the bottleneck of this algorithm. The main idea was that we compared two algorithms, so two formulas for Q. First is we've chosen completely uniform sampling. So whenever we have k vertices in the graph, we assign 1 over k to each vertex, and we draw from that probability. And second, we thought, okay, why not use something which is related to W, and we use probability which is proportional to W, which simplifies the computations, which simplify the formula. And the idea behind the second algorithm is that whenever something has larger weight, then probably this path would have greater probability, which of course eventually maybe not true, because we can have certain dead ends, right? So first step could be with high probability, and next steps could compensate that could be with very low probability. So it is always going the greedily. It's not the way to go. And one thing that we noticed that actually, whenever we use this algorithm, let's suppose that we know from some external knowledge that vertex 1 was always before vertex 2. Then we can introduce this knowledge very easily just by modifying these formulas. So whenever we have, for example, we know that vertex 1 was before vertex 2, and we still have both vertex 1 and vertex 2 in the graph, then this set of candidates, we can exclude vertex 1 from this set, because vertex 2 has to appear in the sequence. And we peel the graph backwards, and we just compute the averages of that. Okay, so we have these formulas, and we run these linear programs. We got certain results, and that these results, actually, whenever we had this LP approximation, this is an upper bound on the integer program, and the integer program points out how much precision, on average, can we squeeze out from a given graph when we require certain density to be at least equal to some certain value. So how much of the order we can recover? How good are we guessing whenever we set ourselves that we need to guess at least a given number of pairs? Okay. And here we compared it so we constructed a few algorithms, and it was investigated before. So for example, as Wojtek investigated other model that he used with quite good results, greedy algorithms, sorting by degree, sorting by neighborhood. And we looked at it, and they were unfortunately on biological networks, they were not so good. But we thought that, okay, we have PUVs, and PUVs are, as I told you, quite good proxies for the probabilities that U came before V in the order. So we need somehow to use this knowledge, and we came with two simple algorithms. First is that whenever we are above some threshold, we assume that it is the case that U came before V. And another is that we take all the PUVs which were estimated, we compute their sums, and this is the weight of our vertex, and we sort vertices in descending order. So we suppose that if the vertex is last, it should have the lowest sum of PUVs, because it's in fact it's the descending order. Yeah, in descending order. Whenever a vertex is last, then it would have PUVs, which would refer to the order which is against the true ordering. So we would expect that it would turn out to be greater than typical vertex taken from the graph. So it's the sum PU should be quite large. Okay, and this was the general framework that in principle can be applied to any graph model. And we decided to apply it, of course, to duplication divergence model because we have lots of symmetry and techniques based on degree and greedy perform very poor. And here you can see the number of automorphisms. In fact, this is for synthetic graphs on 2000 vertices, if I remember correctly. And here you see that there is quite large area of parameters whenever where we have large number of automorphisms. And this is measured in logarithm number of automorphisms. So that's why you have fractions here, right? And that means that if you have logarithm number of automorphisms, which is, let's say, 10 to the third, and these were natural logarithms, that you have actually tons of automorphisms. So, and we are usually within this range that either P is quite, let's say, in our experiments, the results were between 0.5 and 0.9, and R was between 0 and 2. So, and of course, our networks are greater, and as the networks go greater, the whole violet-blue area becomes large, right? So the whole picture becomes more violet. Okay, and here are some results. First, we took the small graph. So for 13 vertices, we were able to compute the exact curve. So to solve the integer programming and in fact, integer programming and linear programming came out almost exactly identical. So we put only the one result here. And given the exact PUVs, we got red solution. And then we assume, okay, let's say we run these two techniques of importance, so importance sampling with two distributions, and let's see what will come out. And it turns out that if we use a very naive uniform sampling, it has better convergence in practice. So with high probability sampling, I guess there are lots of dead ends at the early stages, and the convergence is really low. But whenever we use local uniform sampling, okay, it may be the case that we are far away because we draw lots, unfortunately, but in an unfortunate way. But here we have convergence quite fast in practice. Okay, even though 13 factorial, so I guess it was 10 factorial, if I remember, because the GT0 was equal to 3. It's significantly higher than 1000. Okay, and then we took local uniform sampling as our benchmark, and we ran on some larger graphs. So here we have some larger graphs, and we used degree-based techniques, which are with circles, and these PUV algorithms with different kind of threshold and different, so with different threshold or different parameters. Here we have sorting by sum, and then grouping in clusters of size C. So of course, this gives some kind of total ordering. This gives us 10 clusters, and this gives us 5 clusters. So we can here we have threshold, which dictates how many pairs are comparable, and here we have size of our clusters. And as we see, estimations of our PUVs algorithms are quite good. Degrees, okay. So here of course you have 0.5, which is purely at random. So this is the lowest point. I guess going below 0.5, it's unexpected case. Does not make sense because you can just flip the results, right? And any algorithm, there is no sense in devising an algorithms which have expected value below 0.5. Okay, but we see that there is a certain improvement. Okay, and the third part, third problem in this talk is compression. And for compression, in general, this is a bit more algebraic problem, but here we are confronted with this case that we have model of pure duplication. So we do not have R, we have only parameter P. For simplicity in the analysis, we assume that the starting graph is asymmetric. And we have special case with when P is equal 1. So it was our starting from our workhorse for this model. And we see that whenever P is equal 1, and we have graph which is asymmetric, then starting number of automorphisms is 1, and at each stage of the algorithm we create a copy of existing vertex. Okay, so we have a certain groups of vertices which we call orbits, and two vertices belong to the same orbit if they are descendants of the same vertex in GT0. Of course, we cannot recognize whether a vertex was copied from a vertex in GT0 or another vertex which was added later, because they are all the same. And this has a straight connection to problem of urns and balls. And we have T0 urns at the beginning, in each urn one ball. And since we draw uniformly, we pick an urn proportionally to the number of balls it contains. And instead, you're probably all familiar with urns and balls model in taking out certain balls. Here, we throw another ball in this urn, and we repeat this process until we have T balls. Okay, so starting graph on 6 vertices may look like that, with some edges in between. And we add a new vertex and create as a copy of a second vertex. Then we add another vertex as a copy of the first vertex. Then we add another vertex, which is a copy of a second vertex. But second vertex in GT0 may not have been its parent. And of course, by this, we can define relation of ancestry. We can define an orbit. Of course, if there are at most T0 orbits in G, and if graph is asymmetric, there are exactly T0 orbits. So there are exactly T0 urns. And if we have asymmetric graph, then of course, they belong to the same orbit, if and only if their neighborhoods are identical. Okay, and we have this ball and urn model, and we have each urn containing one element at the start, and we perform this process. And it turns out that it is a process which was already described in the literature. Its distribution is so-called Dirichlet multinomial distribution, and it can be described using this formula, where we have certain beta function, right? So here we have Euler gamma functions I was talking ad nauseam last time, and beta function is just a product of certain beta functions. And of course, this is distribution which has T0 dimensions. And the question is how we can estimate that. We have this object, this vector describing the count of balls at each coordinate. And it is sufficient to see that it describes the structure of a graph generated by this model. And whenever we are told, so we have original graph, which can be stored on a constant number of bits. And we have additionally this vector, then we just can recover the whole graph. Okay. And it turns out that if we look at the marginal distribution, the marginal distribution is another distribution which is well known. It's called beta binomial distribution. And the trick is that if we want to get the entropy of the graph, so we know that there is a bijection between graphs and these descriptions. So actually between unlabeled graphs and these descriptions. And these, by simple calculations, we can compute that this is the expected value of logarithm of value of each coordinate. And since all coordinates are symmetrical because they all started with exactly one ball in each urn, that we can turn it into a sum. And we just need to concentrate on marginal probabilities. And marginal probability tests. So marginal probability has much nicer formula. And of course, we have two problems. That this was for unlabeled graphs. Yeah, so we were not considering labels which are from 1 to t, and which we identified with the order in which vertices arrive in the graph. But we also sometimes want to have certain labels, for example, numbers from 1 to t. And we would like to compress them as well. Okay. And both Wojtek and Abraham Magner, derived this simple formula under one very important assumption, that suppose that we have an unlabeled graph, and it has to be the case that all ways to generate this unlabeled graph has to have the same probability. So regardless whether we add first vertex 1, 2, 3, 4, or 4, 2, 3, 1, whenever it's feasible, so it is whenever all these ways of creating graph have positive probability, they have to have the same probability. And when it holds, we have this formula that the difference between their entropies is the difference between number of automorphisms. That's why we are investigating the automorphisms in the previous case. It's also important parameter in this sense. And between another parameter, which is gamma. Do not confuse with Euler gamma function. Gamma function means here it means actually the number of permutations which are positive probability, which have positive probability. So number of ways of adding vertices to the graph that we arrive at the same structure. Okay. So as for computing automorphisms, it is the case that whenever two vertices are within one orbit, we can swap them. Whenever they are within different orbits, we can never swap them in our automorphism function. And this is quite obvious to prove. Okay, whenever we have these arrival orderings, then we can swap orderings whenever two vertices are in the original graph, because in T0 we can do whatever we want. And the second case, if they are not in T0, then we can swap them too. So the only condition is, because if we here under this model, we add only copies of existing vertices. So the only condition that really limits us is at least one vertex from each orbit has to be in the original graph. Since original graph has T0 fixed, we know that exactly one vertex from each orbit. So we can swap vertices in T0, we can swap vertices in GT minus T0, and there is a third factor. Then we can swap the original vertex, which was in GT0, we can swap it with any vertex from the same orbit. And it would still be a valid ordering, valid arrival ordering, right? Okay, so using these two formulas, we have the left-hand side and the right-hand side, and now we need to find the left-hand side. Left-hand side is in this case we just find one part of it. So as I told you, the whole structure of the graph can be described with this vector. And this vector has known formula. I suppose that minus here is unnecessary. Right. And with all these three in hand, we can compute h of g of t. So now the entropy for labeled graphs. And since we have the formula for the probabilities, we have the whole probability distribution. The trick is just to apply it and consequently go through the expected value, since we know both the distribution, which is beta binomial, and we know the formulas, right? So we have these values, and eventually we can arrive at these estimations. Today, as I told you, I spared you the algebra, and we arrived at the point where we know that the entropy of the structure is proportional to logarithm, and the entropy of the whole labeled graph is proportional to t. Here, it's natural, because whenever we consider what is the obvious way to compress the graph, the labeled graph, we can say, okay, let's give vertices in T0 number from 1 to T0, and then let us have the vector of vertices, so the vector of labels, denoting the ancestor of, so on the ith position is the number of vertex in T0 it was copied eventually from, right? So we have a vector of T minus T0 numbers. Yeah, so we have, okay, so we have vector T minus T0 numbers. And for each, we have more or less logarithm of T0, right? So because we have to write T0, T0 in binary requires block T0 bits. So we would expect that after compression, it would be something proportional to T log T0. Okay, and we know that h of T0 is, so the T0 of harmonic number is close to natural logarithm. And of course, we have to multiply it by logarithm of E to go to the binary logarithm. And the same go here. And here logarithm denotes binary logarithm. Then if we want to just describe the structure, we take this vector, and this vector has T0 coordinates. At each coordinate, we have a number from 1 to T. So we can write it on log T bits. So we would expect it would be T0 times log of T. In fact, we can squeeze a bit here. We can squeeze a bit here because this is strictly less than logarithm. And of course, there are some lower order terms. And the interesting thing is that due to the amount of symmetry, these really diverge. And all previous classes of graphs which were investigated before had these very close to one another, because usually the proof proceeded in that way that under this model, this graph is asymmetric. And if it's asymmetric, then this quantity is very small. And since this quantity is very small, then these two quantities have to be close to each other. Okay, and then we had this graph compression because we have probability distribution. Then we can apply something which you may all probably know called a arithmetic encoding. And arithmetic encoding is guaranteed that if you applied it properly, that you compress graphs up to 2 bits within entropy, right? So entropy is the lower bound for compression, and we can compress within 2 bits larger, right? So the average word is less than entropy plus 2 bits. Okay, and the trick is that, of course, in both cases, we encode a sequence of cardinalities and a sequence of numbers of our, or IDs of our ancestors of vertices, just like we would do it in naive way, but we use slightly different probabilities. So we do not write all using log n, so log t bit or log t0 bit numbers. We slightly optimize on that, and that's why we can match the entropy bound. Okay, and we implemented it, and it turns out that so all in all, it behaves well, and even the error. So of course these are average values. So the question is, how about convergence? But observable convergence was pretty good, that within few thousand samples, few hundred, yeah. So within, let's say, 10,000 samples, we arrived within 2 bits of entropy, which confirmed that we are good. And of course, the curves are really close to each other. And the trivial algorithms is obviously outperformed. Yeah, and that was for the structural entropy, and it grows even to the negative I as the logarithm. And here we see that the growth is linear. And similarly, so we had certain problems. We had here we went out, but here we just guessed that our estimation of h of g has a certain constant factor that I didn't include in the final formula, and that's why we went off. Okay, so this is basically it. Only the one thing that I want to mention, that why we did it for p equals 1, because that was our starting problem. In fact, back over 4 years ago when I started working on this problem, and we're still tackling the problem whenever compression whenever p is between 0 and 1, because unfortunately the crucial property does not hold. So whenever suppose we have these two graphs, labeled graphs, then they have different probabilities. And it also can be the case that two graphs have positive probability and the probability is still different, right? So I guess I couldn't find example on 4 vertices with that, but I guess it's important to know that, for example, here you can copy vertex 4 both from vertex 1 and vertex 3. And in certain cases, it might be that you can copy from certain vertices, but not from the others, right? So the order does matter, and in fact, in this model, does matter a lot. Okay, so that's all I wanted to say, and thank you for listening. I wonder whether there are any questions. Hopefully, this time was clearer, because at least there were images, not unlike the last time.
So any questions? That was a presentation, Krzysztof. Good.
Thank you. Okay.
Okay, I think you exhausted everybody. So,
yeah.
Okay, I will call in 5-10 minutes on Skype. Thank you,
okay,
guys.
I'll be ready.
The next week, we're going to have something about quantum, and Dr. Padakantla will talk. Okay, thank you.
Thank you. Bye.
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 Goodbye.
Thank you. Goodbye.
Bye.
Bye.
Thank you. Goodbye.